is visiting us from Austin, Texas, and as you can tell, we have very nice weather here. It gets warmer. It didn't used to be that way. And we very much look forward to his first presentation about white dwarfs that might be polluted. After that, we hear from Barak Rom, who is a student visiting from the Hebrew University. Where is Barak? Oh. And he will tell us about dynamics and transients around the supermassive black holes. After that, we'll hear from Lamman, our own graduate student who just received the honor from the National Academy of Science. Congratulations, Claire. And she will tell us about the multiplet alignment, tracing landscape structure with small correlations. And finally, we'll hear from a sabbatical visitor here, Ralf Klessen. Where is Ralf? Oh, over there. Visiting us from Heidelberg, and he will talk about modeling the local bubble. Keith, please go ahead.
Great. Can everyone hear me? I'm not using the mic. Should I?
No, we need the mic for the report.
Yeah. Rookie mistake. Okay, is that better?
No, it's not on. Is it on?
Nope. Another rookie mistake. Okay, that's on. Wonderful. Thank you all for joining. My name is Keith Hawkins. I'm at UT, where it's currently 90 degrees today. Not much nicer here. So I'll be talking about some work that we just completed on looking for polluted white dwarfs and other treasures in the Gaia data set. This is a paper written by my student Malia, who is in her 4th year of graduate studies. And this goes back to this question. I'm a galactic archaeologist. I focus on stellar and galactic astronomy, but I've also been kind of tapped in a little bit into the world of exoplanets, thinking about, in particular, how do we know the composition of an exoplanet, particularly its interior. I'm mostly interested in stellar atmosphere compositions, but this is kind of another interesting question to me is how do we actually learn about the interior composition of planets, and does it correlate at all to not only stars, the host star that the planet is around, but does it change as we move through the galaxy? Is a planet in the inner galaxy different in its interior than a planet in the outer galaxy simply because of the material that it's made from? And this is part of my broader goal in my research group to start thinking about constraining the galactic habitable zone. So thinking about applying the concepts of galactic and stellar archaeology to the exoplanet community and world. So the quintessential way to figure out what is inside of a planet, you can't obviously go up to the planet and scoop up some of the material and learn about it, but what you can do is watch the material of that planet be singed onto a white dwarf star. Why a white dwarf? Because white dwarfs have spectra that are fairly simple. They're really hot. They usually have broad hydrogen or helium absorption lines. And so any other metals that you see on the white dwarf will be from, say, a rocky planet. And so there's a high impact of finding polluted white dwarfs because they actually tell you firsthand what is inside of a planet. And you can imagine if you can determine, for example, what's inside of a planet and measure the abundance for many polluted white dwarfs across a wide variety of environments in the galaxy, then you can actually start to begin to, at a population level, to understand what planets are made of around the galaxy. So the question that we asked when I got tenure, because this was a little bit of a risky project, is can we find polluted white dwarfs in the Gaia data, which is very low resolution data? And many white dwarf folks that I talked to about this said absolutely not. The data spectral quality is too low. And so the way we typically find a polluted white dwarf is we look for them in large spectroscopic surveys where we have white dwarfs, and then some of them, tens of % or so, just happen to be polluted. Gaia has moderate low resolution spectra, R of about 11,000, for about 1 million stars down to G-band of 19. This is too bright for there to be pretty much almost any white dwarfs, so Gaia may not be able to help us find polluted white dwarfs. But it does have a low resolution spectrograph, and instead of a 1 million spectra, it has 220 million spectra. So maybe there'll be Gaia, maybe you'll have some polluted white dwarfs in that. And so we said, why not use these? The problem is, of course, these are very low resolution, R of 70, which is it spectra anymore? I'm not sure. Or is it spectrophotometry? Anyway, irrespective of how you answer that question, the question is, can you use that spectrophotometry to really find polluted white dwarfs? To give you a sense for what this looks like, this is a normal white dwarf spectrum. Notice that it peaks in the UV. You've got the broad hydrogen Balmer lines. And then this is what a polluted white dwarf looks like. So significantly different spectral quality, different spectral features. These are like calcium H and K, magnesium triplet, and so forth. And so the challenge, oops, I did that. The challenge is going from a spectrum like this is R of 2000, like the spectra in the previous slide, to like this. This is an R of 70 spectra from Gaia. And so we took all white dwarfs in the Gaia data set. We took all of them, and we can't look at all the spectra, so we actually use a machine learning algorithm, which we particularly use dimensionality reduction and manifold learning, UMAP specifically, to plot the spectra of all of these white dwarfs. And this is what a UMAP projection of all of those white dwarfs look like. It's highly structured here, but if you start color coding by different things, you can learn what that structure is. For example, you can color by the color of the star, and you find that all the hot white dwarfs are on one side of this map, and all the cool white dwarfs are on a different side of the map. This projection basically says, let's take white dwarf spectra that are similar, it's in the same region of that UMAP space, and spectra that are very different are in different regions of this space. That's all it's doing. So you can actually find hot, cool, and cool white dwarfs in different regions. Turns out that the DOs are at the top, the DBs, which are helium-rich, are here, the DAs are here. But there's also little islands, like an island here, an island here, an island here, here, and over here there will be one as well. And those islands are very interesting. So this is just showing the stacked spectra of the fact that we can separate out DAs and DBs because they have different spectral features. But in fact, if you plot the known polluted white dwarfs, a ton of polluted white dwarfs fall in this particular region of this UMAP space. This shelf in the UMAP space actually is almost all, 95% of the stars there are likely polluted. And there's more than 1,000 candidates in that particular region that are not known to be polluted currently, but we think they might be. This is the stacked XP spectra where you can actually see the significant calcium H and K absorption here. Even in R of 70, it's extremely obvious. And you might ask, does this actually work? Can you use this map to find the polluted white dwarfs? Well, we actually observed more than 70 of them with the Hobby-Everly telescope low-resolution spectrograph. And this is what their high-res spectra look like. Beautiful, beautiful, many, many absorption features, many, many absorption lines here. And so now we're in a position where we can measure the detailed abundance ratios with these follow-up spectra and actually begin to ask the question, does planet chemistry change? The interior of planets, do they change as you move around in the galaxy? This has gotten quite a lot of press over the last couple of weeks and months, but we've actually not only found that they're real with our own surveys, but also with Sloan 5 and with DESI. And finally, I'll just say that I know that I probably should be wrapping up here, but I will say that we have been also looking at what these other regions of the UMAP space look like. And so this is the UMAP projection colored by Roue, which tells you the red here is binaries, the blue is non-binaries. And the variability, this is how photometrically variable the star is. The red means it's very photometrically variable, and the blue means it's not. There are regions, for example, like this, where all of the stars in the DA region just suddenly become more photometrically variable. This is the instability strip. So we found the DVs, the white dwarf variables, and in fact, we actually have a way of separating out white dwarfs from mass, because the spectra are mass, or have some information about the mass. And so one of the things we're doing now, my student has actually chosen all of the DVs, which is in here, the DAVs, and she's looking at the high mass ones, because those are the stars where they're starting to crystallize in their cores. And so using astroseismology, she's actually learning about crystallized structure just from this UMAP projection and knowing where they are and doing follow-up information. We also have found areas where not only they're photometrically variable, but in addition to that, they are astrometrically wobbling around, which tells us that they're also binaries. So think about things like double degenerate binary systems and white dwarf M-dwarf binaries. And one of the things that we're working on now is, in fact, finding binary systems that are also polluted. And so you have a polluted white dwarf where you know about the chemistry of the planet, and a wide binary FGK star where you know about the surface abundance of the star. And so suddenly you're in a position where you can correlate the planet's chemistry to the star's chemistry. And so that's what we're doing right now with this UMAP. And you can also search for different types of unique white dwarfs. We've been looking into these really cool DQs with beautiful swan bands, all picked out beautifully from this UMAP projection of more than 100,000 white dwarfs. And finally, I will just end with saying, this is only the start. There's plenty of data here. There's plenty of ways you can interpret this map. And so your ideas now can go here. That's it.
preceded the white dwarf, and it probably consumed all the rocks that used to exist within an AU or so. And so the question is, where does the rocky material come from? And the natural origin would be the envelope of the star, that somehow the heavy elements reproduce the rocky material. And in that case, you would just measure exactly the abundance that the stellar envelope had. So that is one thing that you can check is with respect to the origin of this rocky material. Could it be that it came from the envelope of the star, or was it something else?
We should actually be able to tell that with the FGK stars that are in wide binaries with these polluted white dwarfs. We only have known of a few of these types of systems, but this study, we actually have found like tens of polluted white dwarfs now in wide binaries with FGK stars. We're getting follow-up spectra of the polluted white dwarf with HET, and we have a southern campaign with those from the Institute of Astronomy in Cambridge. And we also are getting the FGK stars with the 2.7 meter shell spectrograph at McDonald Observatory and in the south we'll probably get them with Magellan. And so we'll actually be in a position where we can say that by actually comparing the chemistry of the polluted white dwarf, the ratios, with the stellar abundances that we see in the FGK stars.
Okay, many hands. So let's start from the left, please.
So the idea of using the correlations in these binaries is interesting. One thing I'm always worried about is, wouldn't you expect pollution to be coming from the winds from the companion in that case? Or like, how do the sort of relative rates work out if you have a stellar companion that's blowing some amount of material? Or are these such wide binaries that you don't worry about that?
These are pretty wide, like tens of thousands or more AU. I wouldn't expect that to be the case. If it is the case though, what I would expect is that the chemistry of the polluted white dwarf would equal the chemistry of the FGK companion, because it's the winds from that's coming off, or an RGB companion. And so I should be able to tell that from the detailed chemical fingerprint. That's ongoing work. We haven't gotten that far, but we have found the largest number of FGK star polluted white dwarf sample that has been ever found based on this UMAP projection. So we're in a position now to do that, but we haven't done it yet. We're fitting those data.
Okay, please go ahead in the middle. Yeah.
Hi. Isn't it true that the sinking times are fast enough with white dwarfs that that at least within the last couple thousand years the material has accreted on, so it's not typically inherited from any red giant stage?
Yeah, you do know that so it is true that the sinking times are very, very short. That's part of the reason why you know that if the accretion happened, it had to happen recently. It probably wouldn't necessarily have happened from the RGB phase, but it could happen from a wind phase of an RGB companion. You can tell if it's an RGB companion or not based on the direct chemical fingerprints, but yeah, you're right. It should actually have all of that material from the RGB phase, unless you just caught it at exactly the right time, which is unlikely, should have all sunk.
And this is super similar to some work that I'm doing, actually.
Great. We should chat.
Yeah, absolutely. And are you looking specifically for like planet hosting main sequence stars? And what's the distance of these? Are you referencing like El-Badri and Rix's catalog, or are you building up a new one?
Yeah, so this is El-Badri and Rix's catalog, so we're starting there. What was your second question?
Are you looking specifically for planet hosts?
No, we're not specifically looking for planet hosts. The point was just to do this more broadly. I'm coming at this from I started with a more galactic and perspective, and then when I got tenure, I was like, let me try something crazy, let me move outside, so I went to this. And so we weren't looking for anything in particular. Now I'm getting more embedded in the white dwarf community. It might be interesting to do that.
Yeah, absolutely.
By the way, this is not so crazy. You shouldn't feel bad. Was a question on the right side? Please, go ahead.
Yeah, so I'm curious. It seems like you identified a part of this space that has like a really pure sample of polluted white dwarfs. But I'm kind of curious about the fact that they're also scattered everywhere else. And if you ask some of these, questions that you're interested in, these broader questions, like using that particular sample, like, do you have a sense of how we might bias our answers, or do you have a sense of like how we control for how we bias our answers?
That's a good question. So so first and foremost, this area is strongly polluted, and all the strongly polluted white dwarfs really are here. The DAZs and the DBZs are separate. So the DBZs are up here, and the DAZs are down here, and these are the known DZs. So they are different flavors of polluted white dwarf. These are the DZs, so they don't have hydrogen or helium lines. So for that population, we're fine. The problem is the DAZs and the DBZs are mixed with the DAs and the DBs, and that makes sense. And so if we were to work with just DAZs and DBZs, because it would be very hard to distinguish between them, I think we would be pretty biased. So I think we do have to be careful about population level statements that we're making. But with, as far as I can tell, and if there are any white dwarf experts in the room, it'd be really exciting to hear from you, is this field is still relatively newish in the sense of like trying to find large samples of polluted white dwarfs. It's still very difficult to get large samples of white dwarfs, just in general. I think Gaia is one of the largest samples of white dwarfs, which is why we started in this particular.
No, it's super exciting. Yeah, thank you.
And it will certainly have implications for our future sun.
Yes,
Yeah.
indeed. For some.
Let's thank Keith again.
Okay. Yeah. Did it work? Can you hear me? Yeah. Okay. Hi. I'm Barak. As I said, I'm the last year PhD student in the Heidelberg University, and I want to talk up today a bit about the dynamics in the centers of galaxies and how they are connected to the transients that we can observe. So this will be part of the work I do with my advisor, Professor Sari. So just to start with some. To have some numbers in mind, so when we look at our own galaxy, so we have at the center the supermassive black hole with mass of 4 million solar masses, and throughout this talk, I will only consider what's going on within what is called the radius of influence. So in our galaxy, it's about 2 parsec, and in the volume with this radius contains millions of stars. Now, this radius of influence is defined such that the gravitational potential within it is dominated by the supermassive black hole. So essentially, we have all of those millions of objects, of stars and black holes, that orbiting around the supermassive black hole on Keplerian orbits. Now, the picture is not that simple, because this is a very dense environment, and so a lot of dynamical, interesting stuff can go on. So just to here, so now I will start with a bit more broader sense of how we understand the dynamics that's going on there, and then in the time that will remain, I will briefly show some specific results we have for LISA, the next generation space-based gravitational wave detector. So to start with the dynamics, we consider 2 main processes. The first would be 2-body scatterings. So the idea is quite straightforward. We have 2 objects. They pass by each other. They exert gravitational force on each other, which slightly alter their orbit. Now this introduces a characteristic timescale, a timescale to change the angular momentum, which soon will be clear why angular momentum. That goes like that. So first it goes as the orbital period. That can be thought of as the time it takes to the supermassive black hole to significantly change the velocity of the object. But now these encounters are much weaker, so we need much more of them. So we have an extra factor of the mass of the supermassive black hole divided by the mass of the object. And in fact, that goes as the second power because it's a stochastic problem. Right? So these encounters are uncorrelated. Each one can change the angular momentum in a random direction. So it adds up as sort of a random walk in angular momentum. So that will give us a much longer time scale. But now we have a lot of scatterers, so we divide by their number. So that would be typically the relaxation time. And now, as again, we will see, we're thinking about the angular momentum, and we are specifically interested in eccentric orbits. Now, eccentric orbits have much smaller angular momentum, so it's easier to change their angular momentum significantly. So we had here the ratio of the pericenter and the semi-major axis, which accounts for the smaller angular momentum of eccentric orbit relative to circular orbit at the same semi-major axis. So that would be the first time scale. The second process would be gravitational wave emission. So now we just think about one object orbiting the supermassive black hole. We don't care about the cluster. And as it goes along its orbit, it emits gravitational wave, it circularizes, and then slowly descends toward the supermassive black hole. That will give us a second time scale, a time scale to shrink the orbit. And first it will go more or less as the orbital period at the horizon, so the Schwarzschild radius divided by the speed of light, and it goes again linearly with the mass ratio, and a very steep dependence on distance. So it goes as the fourth power of the distance. So that will be the two processes we consider, and that's introduced two timescale. Now, it's a lot of details, and I think it's very useful to visualize what's going on in sort of a phase diagram that looks like that, and I want to go over the details here. So first, in the x-axis is the semi-major axis in units of the radius of influence, and the y-axis is the pericenter, again in units of the radius of influence. So it's sort of so it's analog to a phase space of energy and angular momentum, but we think of it in the semi-major axis and pericenter. And it's triangular because by definition the periapse is always smaller than the semi-major axis. So that's the big picture. Now we can start by at large distances. Typically scatterings dominate. I said the gravitational wave has a very steep dependence on the distance. So here the scattering dominates, and at small distances, gravitational wave takes over. And we have this separation, the dashed black line, which is where the two timescales are comparable. Now, that would be the first division. And the second one, which is here corresponding to transients, where we are going to. So it's this red line. So that would give us some minimal distance an object can reach. So that would be sort of a destructive bound. So for stars, it would be the tidal radius. For black holes, it would be the mostly bound orbit. And so below it, there are no orbits reside. And now, so with that division, we can start to see how orbits evolve. So for example, we can start with some object here at the very outskirts of the cluster. So it's in the two-body scattering dominated region. It starts to diffuse in angular momentum, so do a random walk in the pericenter. So it here go up and down. Now some of these objects can be pushed to such high eccentricities that they will reach here. So they will reach the destructive bound, and that will be the origin of TDEs for stars, for tidal disruption events. So stars on a very eccentric orbit that pass too close to the supermassive black hole and get tidally disrupted. Or in the context of black holes, it would be plunges. So again, a stellar mass black hole that just falls quite rapidly and swollen by the supermassive black hole. When we go to more bound orbits, so the object that starts here, again, it's in the scattering dominated region. It diffuses in angular momentum. But now, before hitting this destructive bound, this red line here, it moves to the gravitational wave dominated region. So here, the orbital evolution is significantly different. Now, it starts to circularize, so more or less constant pericenter, but a decreasing semi-major axis. And then it's slowly falling toward the supermassive black hole, typically with very small eccentricities. And that is associated, and this would be the formation of EMRIs, extreme mass ratio in spirals. That could be an EMRI of black hole, so a stellar mass black hole merging with the supermassive black hole, which will be a primary gravitational wave source for LISA. Or it could be a stellar EMRI, so the same orbital evolution, but by star. Then it can shed mass to the supermassive black hole or can interact with a disk that is there, and that is associated with this recently discovered transient in the X-ray of quasi-periodic eruptions. So that's the idea, and you can see that within this dynamics, we can really discuss quite a wide range of transients, of gravitational wave sources, and electromagnetic sources that we are seeing now or are expecting to see in the near future. So that will be the broad dynamics. And now I want to focus on some results from a recent paper of ours about EMRIs as gravitational wave sources. So to do that, the dynamics are not enough. We need to also say something about the distribution of black hole. Essentially, we need to know how many black holes we have at each semi-major axis, and then we can calculate the flux. We can calculate the rate of this black hole entering the gravitational wave-dominated region, and we can know the formation rate of EMRIs. Okay. So now, because of the interest of time, so I will skip our calculation of the steady-state distribution. I'll be happy to discuss it later. We have some new analytical derivation for the global steady state that includes the effect of scattering and gravitational wave. But again, I will not go into detail here. But the idea is that we have it. We know how many black holes we have at each semi-major axis. And then we can have the rate of the EMRIs rate per galaxy. So that would be the intrinsic rate. And now we can take it a step forward. So we can assume now all galaxies are obey this intrinsic rate. We can change the supermassive black hole according to the supermassive black hole mass function. And then everything is scalable, assuming the m-sigma relation. So we have all of these 3 steps. And then we can have predictions about what LISA will see during its 4-year mission time. That looks something like that. Sorry, so here I present in the y-axis the characteristic strain of the emitted gravitational wave, and in the x-axis the frequency. So first, the thick black line here is the LISA sensitivity strain. So any source that crosses it will have SNR greater than 1. And now here, the thin black hole lines, they're all, this is just a visualization, so they are all single M resources that we evolve across along 4 years. And they just here to the visualization, but our results are actually summed up by these colored lines. So these colored lines are contours of number of sources. So how to understand them? So let's start with the line that corresponds to 1. So this line tells us that we expect to, at each logarithmic frequency bin, to see one source brighter than this limit. So in the whole LISA band, we'll see few sources, very bright, very nearby, with very high characteristic strains. Now, as we go for lower characteristic strain, we are seeing further out to the universe, and we can see more and more sources, all the way to hundreds of thousands of sources. And the color bar gives us the average redshift, so you can see we get to a redshift of a few. But now, from all of these hundreds of thousands of sources, not all of them will be resolvable. Detectable is single sources. So to do that, the current data analysis estimation is that we will need a higher SNR, so not SNR of 1, but rather SNR greater than 20. And when I mean resolvable, I mean that it can be detected as a single source that can be localized in the sky. I'm just finishing. It can be localized in the sky. Its parameter can be extracted. And so for that, we here a conservative estimation of SNR 20, this red line, and only the sources above it will be resolvable. So we'll get, in 4 years, 2,000 resolvable MRIs. The rest, the great majority of them, will give us a background stochastic noise that will add up to another noise term for LISA. So that I'll also be happy to discuss. Yeah, and with that, I will finish. So the idea is we blend in dynamics and some assumption about the distribution, and we get predictions for transients. Here I talked about gravitational wave sources, but with that I leave you. But it can be discussed to much more, to electromagnetic transients. Also, if we consider binaries, we can talk about hypervelocity stars. We can talk about the formation of LIGO mergers and all. So I'll be happy to talk about all of these topics. Yeah, and with that, I'll finish. Yeah.
Can you say anything about the Milky Way galaxy? Because we are much closer, of course, to the center of our galaxy than on average in the universe. What is the chance that during your career you will see something, given the stellar population that we know is there must be some population of black holes, stellar must be.
Yeah, I think that to get for there an M resource, we need to be very lucky. It would be amazing, but I won't bet my career on it, let's say. But I think for sure there are like a guaranteed science we will see there. So in this plot, I have it's already included. Yeah, so we see here, it's also related a bit to the white dwarf we heard about before. So this would be the white dwarf galactic noise, which would be very anisotropical. So we will definitely see that, and we will see a very, I think, interesting white dwarf signs that we'll definitely could do. But specific M is very close to the supermassive black hole. It would be hard to expect any. It would be observed from our galaxy.
It's difficult to expect within a decade.
Within the next 20 years, let's say, until LISA will launch, and
well, nature has its ways to surprise us.
I hope, man. Yeah, it'd be amazing.
Ralf.
Speaking of surprises, I'm wondering what the associated mass accretion rate is with your mechanism. And the background of my question is the accretion rate onto supermassive black holes in the early universe, which we know should be embedded in very dense star clusters. Often these star clusters are expected to have members that are very tiny, so the radii are much larger than the standard main sequence radii that presumably you are using. And so this mechanism that you described could be an important way of providing mass to gobble up the central object, by the central object. So I was wondering whether you have A, calculated the mass accretion rate associated with this stellar derivative process, and B, how it scales with cluster properties.
Yeah, so we have the, we didn't do the full calculation. We are now working on stuff like that because here, yeah, there's a lot of interesting questions. First, there is this different, in the context of black hole, the difference between plunges and aneurysm. So in plunges, the whole black hole will be just swallowed by the supermassive black hole. And I think usually that's kind of related to our result about the distribution. So usually they assume that the plunges are much more common and they dominate the accretion rate, and then there we'll probably not see them because their gravitational wave signal would be just like bursts, so we will miss them.
So my question is not about would we see it with gravitational wave experiments, but what would be the mass growth? Because we see the supermassive black holes.
Yeah.
Is this an appreciable effect compared to standard gas accretion?
Yeah, so I think only when consider only here we do the calculation only for the black holes, and then it would be quite small. So, but what we are working on now is to really have more realistic distribution of stars, and then we can get the mass accretion from these processes of stars, stellar aneurysm, and also from the black holes, and that would increase it. And then, but I don't have the exact number now. It's on progress. But yeah, it's
So
definitely.
Ralf, the answer to your question also depends on redshift, because early on there was much more gas in galaxies that could grow the center of black holes. But nowadays there are galaxies that have very little gas, and most of the growth is by emergence.
Absolutely. So the question is this something we need to take into account when we worry about the formation of supermassive black holes?
Potentially, but we don't know exactly the history, and of course this is one way of probing it.
Yeah, so we will have estimation. We are working on it. But it's, yeah, I think it would be also very important what the stars are doing. And here I focus on the black holes.
For the stars, you're sort of already counting them, right? Because their accretion is luminous. And so when you look at quasar activity or black hole activity in the local universe, you can ask what fraction of that is fed by tidal disruptions of stars. But it's still luminous, and so it's still represented when you count. But for the black holes or the compact objects, they can add without necessarily being.
Okay, we need to move on, and let's thank Barak again.
All right. So initially, small perturbations in the very early universe gradually grow into large-scale structure, and as they do, baryons flow along filaments, ignite, and form galaxies. I study the very largest structures in the universe, but I still care about little things like galaxies because they still retain some subtle memory of the cosmic environment from which they originated. This can be a real pain for a lot of measurements in cosmology, like I've talked about before at the CFA, but it can also be useful, and that is what I'll talk about today. One way to quantify some type of correlation between galaxies and large-scale structure is known as intrinsic alignments. And the general trends we see are that the long axis of any sort of elliptical object, like a galaxy or a halo, is aligned with the stretching direction of the tidal field. So you can think of it as with a filament pointed towards clusters. And then for blue galaxies, it's really the spin vector that's aligned. If you've heard about intrinsic alignments before from anyone besides me, you probably know it in the context of systematic and weak lensing surveys. But intrinsic alignments contain a lot of extra interesting information. When you're mapping the underlying structure of dark matter, it's most common to use the positions of galaxies and a two-point correlation function, so the probability that a galaxy has a neighbor at some separation. Intrinsic alignments carry additional information about the direction of gravitational forces at each point. So since these trace the tidal field, in principle, they can be used to detect anything which leaves an imprint on the large-scale distribution of matter. People are excited about this and have looked at using it to probe multiple cosmological effects, some of which can't be detected with traditional two-point correlation functions. So these are sensitive to parameters of dark energy, gravity, and physics of the very early universe. So this all sounds great. Why haven't we heard about people using intrinsic alignments as a cosmological probe in surveys? The reason is because using it in practice is not necessarily practical. It's very subtle. You need lots of galaxies. A lot of galaxies don't even display intrinsic alignments. Currently, there are no direct detections of intrinsic alignments in any blue populations or galaxies beyond a redshift 1. Ideally, you have positions of galaxies with spectra and also high-quality imaging. And even when you do have high-quality imaging, the effect is so subtle that systematics and imaging just really can wreak havoc on what you're trying to measure. So I'm working on a new approach where we look at the alignment of very small ensembles of galaxies, using only their positions, so we don't need to rely on determining the shapes of individual galaxies. The perfect data set to test this in is DESI. We're using spectroscopy to measure the redshifts, and therefore distances, to millions of galaxies. Redshift surveys have a very rich history here at the CFA, including the CFA Redshift Survey, which provided some of the first clear evidence of galaxies tracing large-scale structure in the form of the CFA stickman. If you have trouble seeing a person in this figure, I may be able to help you out. If you're watching the recording, this is Halloween. I don't dress like this for all my presentations. But with DESI, we've found that the stickman is not alone. The results I'm going to talk about today use DESI's year 1 data, which consists of 14 million spectra, but altogether we're on track to get around 50 million by the end of the main survey. Our main goals are to measure a large-scale structure and its evolution through RSD, BAO, mostly using two-point clustering. This will inform us about the components that drive this structure and its evolution, like gravity and dark energy. But the massive amount of 3D information we have is the perfect data set to explore higher-order clustering, which is pretty much what multiplet alignment is. This is a new way to detect correlations between small-scale clustering and large-scale clustering. So the basic principle is that you can use the orientations of a small ensemble of galaxies instead of individual ones. Multiplets typically consist of 2 to 5 galaxies within about a megaparsec of each other. And we call them multiplets, not galaxy groups or small clusters, because they're not necessarily virialized. So you can imagine that some members of these multiplets are perhaps still in the process of infalling. However, like galaxies and clusters, we expect that they're governed by similar dynamics and still retain some memory of the cosmic environment from which they formed. To explain the estimator itself, let's begin with a cartoon of the underlying dark matter web, and on top of it we'll place a multiplet of galaxies with some net orientation. This is measured relative to the positions of single galaxies, which are used as a proxy for the underlying matter distribution. We measure the angle between them as a function of separation for many pairs of a multiplet and a tracer galaxy, and then measure that as a function of separation. So if you're used to seeing things with higher order clustering, this is similar to a very squeezed 3-point correlation function. The y-axis on my plots will show cosine 2 of this angle as a function of r. So if multiplets on average have some tangential alignment with a large-scale structure, this is -1. If you have maximum tidal alignment, this is +1. And if there's no correlations, you'll see 0. As you might expect, this signal is really high at low separations and quickly drops off. So I used a trick that a lot of cosmologists do, and I've also multiplied the y-axis by r so we can better see some of the scale dependence of this signal. Here's the measurement we've made with big, luminous red galaxies in DESI. We found a detection out to projected separations of 100 megaparsecs per 8. These are on order of the largest structures of the universe. But the correlations that are giving rise to this signal are rising from the small nonlinear regime, multiplets around 1 megaparsec. We can begin to interpret this by looking at the same signal in a mock catalog created from a dark matter-only simulation and painted with galaxies to match DESI's clustering for this same sample. So generally, on really large scales, we can trust information we get from n-body simulations. We're well into the linear regime. But because this correlation is connected to small scales, it doesn't totally reproduce it. It's much lower, but it actually does match the scale dependence. So here I've just multiplied it, added the 30% onto this signal. And this is a demonstration of how the scale dependence, or the shape of this signal, is tracing the underlying large-scale structure, but the amplitude is a result of small-scale dynamics. This is useful because it means you can make some statement about the underlying matter distribution regardless of what galaxies you're using. And so to really make this clear, here's a measurement of the alignment or the orientations of individual galaxies for both blue samples in galaxies in a very dense region and galaxies in DESI that are beyond redshift 1. These are both 0. We expect this. This is known. But we're using the same galaxy samples. With multiplets, we can detect usable information. It's pretty clear for the dense sample between redshift 0.1 and 0.2. It's a little noisier beyond redshift 1, but it's a detection which has not been done with traditional estimators. And this sample beyond redshift 1 is particularly sparse for year 1, but is going to get much more filled out with future DESI data, so I'm especially excited about using this at high redshifts. So previously, measurements and use of intrinsic alignments were limited to samples of bright red galaxies with high-quality imaging. But multiplet alignment opens the possibility of using all galaxies in spectroscopic surveys to trace gravitational shear on very large scales. I'm now developing this for a variety of applications. To quickly rattle off a few that are most relevant for upcoming surveys. This is a clear instance where n-body simulations fail on large scales, so it can be a useful test of semi-analytic models, which are trying to accurately produce connections between large and small scale clustering. It can be used to measure how the nonlinear behavior of intrinsic alignment and how it evolves across cosmic time, which is useful information for intrinsic alignments in weak lensing surveys. It could be used to trace very large-scale modes through small-scale clustering in a way that is sensitive to different systematics than other estimators. And it could be used to just map tidal shear. So with weak lensing, you're getting a measurement of tidal shear, but from a result of matter that's all along the line of sight. With multiplet alignment, you're having a measurement of a localized tidal shear. So you could use this to measure gravitational shear even at very large redshifts. So we're currently looking at what might be possible with some of upcoming data and future surveys. This was just a quick taste. So to see all the details of our detections in DESI's year 1 data and initial modeling, you can see this paper. And if you want to know more, but you don't care about all the details, you can also find an accessible summary, which is linked in the archive comments section. So overall, galaxy multiplets can uniquely trace the large-scale tidal field in a way which is independent of the most common issues associated with using alignments of individual galaxies. This has promising cosmological applications, but overall, I think it's just a really interesting demonstration that even well into the nonlinear regime of formation, galaxies preserve some interpretable memory of their cosmological origin through tidal fields generated from the largest structures in the universe.
This was a record.
I
Perfect.
didn't expect, I really thought I was going to go over it.
You're amazing. Anyway, but as you mentioned, this statistic that you described is equivalent to the squeezed limit of a 3-point function.
It's not exactly.
Not exactly, because it's non-linear on small scales, but also not exactly mathematically, you're saying?
Yes, because you, in the case of where you have like 4 galaxies, the position of one, it's functionally it's very similar, but it's
so my question is, I mean, often the bispectrum of 3-point function is used to set constraints on non-Gaussianity. Is it impossible to use your analysis to do that, or?
No, it could be. People have looked at using the intrinsic alignments of galaxy clusters to detect hints of non-Gaussianities. This could be useful because you even have smaller sets of objects. Also, the very large distribution of matter large-scale modes are especially sensitive to PNG, and multiplets could be a useful way to measure that, perhaps better than the 2-point cluster.
But you haven't tried to set a limit from that?
No, I just...
That would be a follow-up paper?
Yeah.
Questions? Ralf?
This is great. And I'm wondering about the following thing. I mean, structure formation is very similar throughout the universe, whether it is the universe at large or the assembly of molecular clouds within the galaxy or of stars and star clusters within these molecular clouds. And so I'm wondering whether you have thought about applications to star formation and the interstellar medium, because you have turbulence, you have gravity, the interplay gives rise to shear and to complex structure. And to my knowledge, I think these kind of three-point statistics has not really been introduced to this field. I think there is quite something that can be learned.
That is a really interesting idea, and I've heard of people trying to apply some cosmology estimators at the galactic scales, but haven't thought about this for this application. So.
Maybe Doug knows more.
Yeah, maybe I need to talk with Doug.
Ramesh?
Yeah, this question may be off the mark, but you've got your multiplet, some number of galaxies, and you're looking at its elongation and the relation to where the test galaxy is.
Yes.
Right? That is your cos 2 phi.
Mm-hmm.
Now, you also showed us that there are these filaments, right? The whole large-scale structure puts galaxies preferentially in filaments and knots. To me, it looks like just the presence of filaments is already going to give you a positive cos 2 phi. And you don't need any additional tidal alignment. How do you separate out these two effects? Or are they two different effects or the same?
My cartoon maybe a little bit misleading. We don't make any distinction between the actual positions of galaxies in relation to the cosmic structure. So this is the signal you see as a result of galaxies that are both in filaments and voids. But of course, ones in filaments are weighted more highly. There are catalogs for DESI that try to identify voids, clusters, sometimes filaments, and so cross-correlating this with one of those maps is something I'm interested in. Does that answer your question?
But Ramesh, the tidal field is related to this web. So it's the same. What you're talking about is the same.
Ultimately, yes, but this is kind of the alignment of, you're really interested in how the elongated axis of a galaxy is aligned with respect to the separation vector, right,
Yes.
from another galaxy.
Right.
Right. So maybe they're all coming from the same thing, but it's quantitatively when you're trying to measure it, it's not obvious to my mind at least that they will all be exactly the same. There are different kind of
Yeah.
ways that the effect is being expressed.
Right, so at least with an analogy of individual alignments, within halos you see that that galaxies tend to have strong tidal alignment relative to a central galaxy, but then once they get into halos, in the satellite region, they actually start to have a perpendicular alignment. So maybe that's what you're talking about. In different environments, you might see different physical effects leading to these correlations.
Josh?
Is there any hope of JWST being able to tell us about the formation of filaments at large redshifts? Why the filamentary structure in the first place? Which is what alignments are.
Josh, this is a standard thing in cosmology that you have collapse along 3 axes.
Sure.
The collapse along 1 axis makes those pancakes or basically the walls of voids. Collapse along the 2nd axis makes a filament. And the 3rd axis makes the cluster of galaxies or galaxies at the intersection of those filaments. So it's just a matter of, Zeldovich understood it decades ago. It's just the sequence of collapses that makes the pancakes, filaments, and then objects.
But the question still is measuring when this really formed.
Yeah, so I have measured this in Millennium TNG. This is pretty preliminary, but in all snapshots where there are galaxies, I detect multiplet alignment.
Any other comments or questions? If not, let's thank Claire again.
I think you have the mic.
All right. I'm not dressed up for Halloween, but at least we do have a Halloween poltergeist here. So we go to smaller and smaller scales, and so I would just say a bit about the project that actually brought me to Harvard for this year. I split my time between the Radcliffe Institute, where I'm fellow in the fellowship class this year. It's a fantastic place. It's really very nice. And so I have to augment, of course, the affiliation that are listed here. So the local bubble, I think many of you know what this is about. So Theo, I promised you I take one of the most recent, where's my English? Pictures of the three-dimensional structure of the local bubble. So remember, the sun is embedded in these relatively tenuous, relatively hot ionized bubble produced by multiple supernova over the course of the last, I don't know, maybe 20, maybe 30 million years. And it has a very complex shape. And I think this is something we have learned from much of the work that has been done here, that this is not a spherical bubble, as you know, your favorite H2 region 20, 30 years ago. This is super complex. It really links to the dynamical and the complex and multi-phase interstellar medium. So what I want to do while being here, I want to improve our theoretical understanding of structures like this. And this is certainly not unique. We are embedded, or the Milky Way is like a Swiss cheese. We have neighboring bubbles. We have thousands of these bubbles in the Milky Way. And I think we need to understand better what is the statistics of those, because we need to understand, in a sense, our place in the Milky Way. Because if you think of it, sitting here in the middle, whenever you do galactic or extragalactic observations, all your sightlines go through this stuff. And the question is, what does it do to your observations? And so I really want to start this small sequence of ideas with one of the greatest failures, at least to me. So you all have seen this, and I think this is a fantastic picture. It is the Milky Way as seen by Planck in dust polarization. And so when we have seen in the group this image for the first time, we said, oh, we know a lot about the ISM, we know a lot about the Milky Way. Let's just try to reproduce this. And in case you wonder why you've never seen a good and faithful reproduction of this picture from a theorist, I will try to explain why this is not the case. So this is our first attempt, and now you know why I call this an enormous failure. So we took the Auriga 6 galaxy, so at the time one of the best Milky Way analogs, and we put an observer in different locations at the solar radius. And wherever we put the observer, it looks like that. So what can we infer? We see most of the signal from the actual Voronoi cell we place the observer in. So much of this signal comes from very, very nearby. So you immediately fail reproducing this if you do not have a good, physically faithful and high-resolution reproduction of the solar neighborhood. And this is then what triggered our attempts to actually do that. And what I will show you is, unfortunately, we are not there yet. But we can reproduce certain feature of that, and maybe in a year's time, I'm here until June, so maybe next June I can give you a proper reproduction of this beautiful image, at least in a statistical sense. So how can we do that? So you need to do radiative transfer of polarized light. You need to know a lot about the properties of the dust, about the alignment mechanism of the dust. And I should note that all of that is not well understood. Do the dust grains, they're fractal, they're complex, they're composition align with the radiation field? Do they align with the flow? There's a relative flow between the dust grains and the gas, which can change the alignment properties. And then, of course, there is the alignment with the radiation field. And so you need to understand that quite a bit. And then, if you understand it, you need to do the radiative transfer. So all of this, at least our current understanding, which is coarse, I would say, is incorporated in this Polaris radiative transfer. So if you ever want to really understand or model radiative transfer of polarized dust emission, then I would recommend you to take this code. Stefan Reisli's postdoc in Heidelberg. So what do we know about the local bubble? This is work, not so old. The reconstruction has started by looking at dust extinction maps in the solar neighborhood from Pelgrim's group, but there is much more by now. And again, lot is propelled forward by people here. So this is the latest map that again took from Theo O'Neill's paper. And so with exquisite dust extinction maps, we can now engage in a 3D reconstruction of the interstellar medium in the solar neighborhood. So we can infer from that what the structure of this bubble is. We know roughly the distance to the wall. We know roughly the properties of the wall. We have an idea about the magnetic field in the wall. And so that is a feature that we would like to match. So our approach for the time being is we have these cutouts of a presumably Milky Way type galaxy. It's half a kiloparsec in X direction, half a kiloparsec in Y direction, and maybe 2 kiloparsec in Z direction. And we have put all the physics we know into these relatively high resolution models. They're done with the flash code. We have time-dependent chemistry, cosmic rays, radiative feedback, supernova feedback, etc., etc. We can look at that. We can look for a local bubble analog, and this is the one we picked. It's reasonably well analog. It happens to be burst open at the bottom. And if you look at extragalactic superbubbles, most of them, the larger ones, are all burst open. And our current one, as we have seen from Theo's work, is about to burst open. There's already this chimney where the hot gas kind of squirts out into the northern galactic hemisphere, if you want. So we can do exactly the same. We can calculate the distance to the walls, and we can run our polarized radiative transfer through it because we have all the information we need. We have the magnetic field density, the gas temperature, the dust temperature. If we do Faraday rotation, which is quite cool, we need the thermal electrons, we need the density of cosmic rays. So this is important when we want to link with the X-ray stuff. So eROSITA now gives us a hint of the diffuse X-ray emission from the local bubble. And so that is something we try to reproduce, and we are doing actually quite well here. And so this is the Planck equivalent, however, only focusing on the local environment. So that is what you would get from the walls of the local bubble in terms of the Planck polarization. And it is clear we are missing out on the disk, but we are doing not so badly towards the south and north galactic pole. And we have exactly information where the polarization comes from, how it differs in different sidelines. This is a different projection. And just look at the true data here and our Planck map. And you see we have more structure in the magnetic field than these guys have. It is more homogeneous. So this tells us in these cutouts we are missing the continuous replenishing of the rotational component of the galactic magnetic field. So that is a subtle thing that we just learned. We were not aware of that. We can do the Faraday rotation. As you know, the Faraday sky is highly interesting. It is highly complex. It is reconstructed from looking at the Faraday map or Faraday effect towards about 2,500 different quasars. And I should stop here by telling that unlike the dust emission that comes from the bulk of the disk of the Milky Way, the Faraday rotation comes largely from the walls of the local bubble. So if you ever want to see the E and B mode signal from cosmic inflation, if you're engaged in the Simons Observatory, a South Pole telescope, you better take this into account. And I think we are not there yet to correct for this effect. And so that is one of the things we would like to engage in making better predictions for. All right, go back. I'm done, please.
Able to detect the B modes from inflation if we were to live in a better environment, or you think we are pretty much in the best case scenario?
This has the answer is two aspects. I think we need to understand the statistics of the local bubble. We need to understand the fluctuations as we look in different parts of the sky. I had a very eerie discussion with George Estasio. He told me, I don't care about dust. I just can correct it in a statistical sense. And for Planck map, I think he's right. For the E and B modes, if you really want to find the polarization signal of cosmic inflation, I think he's wrong. And he's wrong in several ways. I think we need to understand the statistics of the dust shield, of the veil in the local bubble. We need to better understand dust physics in the galaxy. I think we are missing so much about how dust grains align that however your favorite model is, this determines your outcome. And we are, like with gravitational waves, we are trying to figure out a signal that is a part in a million, maybe. And so we need to understand the foreground better. And I think
as long as they put upper limits, it's okay. But once they claim a signal, then your contribution will be very important as to whether it's a real signal from inflation or just something they haven't subtracted.
Yeah, but if you have such an uncertainty in the foreground subtraction, and your signal gets completely lost, how good is an upper limit?
So you are pessimistic about it?
No, I think more work needs to be done. And I think it's actually a super cool field to work in because it relates to the microphysics of dust. It brings in Milky Way physics. It brings in lots of physics.
This is very interesting that what we want to learn about the most distant universe is affected by the most local universe.
Exactly, and by things that are micrometers in size. I think this is rather cool.
When we reached our time limit, let's thank Ralf.
As for questions, I'm around.
You around, you mean your office in this building?
Yes, my office is in B232B. So B like Bell, like Ben.
So is it B?
Yes, B232B. So it's down there in some obscure small corner.
Are you around maybe tomorrow? I want to chat with you about a couple of things. So one,
You are here, right?
yeah.
I need to run. I need to run to Redcliffe today, and I need to finish my preparation for the ESC.